So now we'll do some partial derivative examples so we can get a good feeling for partial derivatives. Now, first, consider a function f of xy, which is given by x squared plus y squared. We ask ourselves, what is the partial derivative of f of x? Well, this is the same as asking what's the partial derivative of x squared plus y squared. Now, in this situation, y squared is considered a constant, as discussed previously. So as such, our answer is the partial derivative of x squared plus y squared is equal to 2x. Now, another question we could ask is, what's the partial derivative with respect to y? Similarly, we have the partial derivative of y of x squared plus y squared. In this situation, this is considered a constant, and therefore we have 2y at the end. Now, in this, let us do another problem. Let's suppose our function is f of xy. We have x squared cosine of xy plus y squared sine of x. Similar questions. What's the partial derivative with respect to x on our function f of xy? This is the same as asking what's the partial derivative of x with respect to x of x squared cosine of xy plus y squared sine of x. Here, in this situation, we have a product rule contained within here, but a power rule, but a derivative rule, definition rule, when we have a partial derivative here. So as such, we separate it. 2x cosine of xy minus x squared sine of xy, and by the chain rule inside, we have y, plus y squared cosine of x. Now, let's suppose that we're given a function f of xy, and we're asked what's the partial derivative of x squared e to the y plus y squared cosine of x squared divided by x plus e to the y. We ask ourselves, what's the partial derivative with respect to x of this function? By now, hopefully, we can see that this is the quotient rule. So first, wherever there's x, we take the derivative of it. So 2x e to the y, and then y squared. Over here we have negative sine of x squared. Then by the chain rule, 2x. And we have all this kept from x plus e to the y as the bottom, minus wherever there's a partial derivative, we have minus 1 x squared e to the y plus y squared cosine of x squared. And we divide this all over x plus e to the y, quantity squared. Notice, with the quotient rule, the problem becomes a little more tedious. So as such, finding just simply the partial derivative of f of x, or finding the partial derivative with respect to x is already good enough. For the viewer, try to find the partial derivative with respect to y. Finally, we would explore chain rule. Suppose you're given a two variable function, and let's say it was given by x plus y, just to keep it simple. But x is dependent on t squared cosine of u. Y is dependent on t cubed plus sine of u. And we ask ourselves, what's the partial derivative of f with respect to t? Well, from here, we have to construct our tree branch. So we have f branches off into xy, branches off again into t and u. Similar thing for y. And we have to find the branches that have t in them. So we first go through here. We have partial of f, partial of x. Then we have partial of x, partial of t. And the branch ends there. Here we go into partial of f, partial y divided by partial t. So from here, this is our relation. So from here, the partial derivative of f with respect to x, so the partial derivative of f with respect to t is going to be the partial derivative of f with respect to x, which is going to be 1 in this situation, multiplied by the partial derivative of x with respect to t, or 2t cosine of u. We move on to the next one with respect to y. The partial derivative of f with respect to y is 1, while the partial derivative with respect to of y with respect to t is going to simply be 3t squared. So at the end, our partial derivative becomes 2t cosines of u plus 3t squared. I hope you have a good feeling about the concepts and the derivative rules, and hopefully we can now see that partial derivatives provide us much more work, but in the end and fundamentally, our single variable representation never left us. We simply represent it in more variables. Thank you.